This is the Solom update for February 21st, 2016. I worked 2 days this weekend. I'm getting the A to D converter working on the multimeter board. I'll go ahead and talk about some of the problems I had with it. So here's the board. This A to D converter back here is a Maxim 11060. And when I put it on, I wasn't getting a clock out. And it turns out this is a really super fine pitch part for me to actually do here in my lab. And there was a short. I tested a lot of things, but there was a short on the crystal. So I pulled this part off and I fixed that. And then I ended up pulling this part off and putting it back on about 3 times yesterday. And finally got it talking. Turns out the Arduino code for the ESP 8266 does not support SPI mode 2, which is clock inversion. So actually I had to write a bit bang routine to talk to the A to D converter, and I got that working. And with no delays, I'm able to take a bit banged routine at running a clock at 80 megahertz can take a data sample every 100 microseconds, which is like 10 kilohertz. So that's far in excess of what we needed. And I got everything running over here. I did have some problems. First problem I had was I spec'd out, this is a current sense resistor, and I had a 0.5 milliohm resistor, and that I wasn't thinking when I put that in. It's kind of ridiculous to think that I would actually be able to get that value because of the solder joints involved. So I actually went and with that resistor, I had a gain, analog gain section in here that ended up being about a gain of 200. And I had a note on the schematic that says, you know, this might be kind of noisy. I need to investigate that. Well, it was really very noisy. So we're going to do something else there. I need to increase the sense resistor value, and I'll have to go over with CFV on what's tolerable for that. Right now I just have a piece of wire in here. This works out to be about 7 milliohms. I got all this functioning today. Yesterday, this is the voltage scaling. This is a 10 megohm resistor. And then right here I have a zener diode that protects the input from overvoltage. And then these are the switch banks that I switch in for the voltage divider. Then the next thing that I ended up fussing with was when I put this zener diode in to protect the input to the op amps. I turned the voltage on. I turned it on real slow from 0 to 10, and while I was watching it ramp up to 10, this thing actually physically smoked. This is a 10 megohm resistor, and so I smoked this part. So I fussed around a lot, and I figured out that this surface mount solder for this big 10 megohm part was shorted underneath there. So I was actually putting a 3.3 zener diode right across the power supply, and that's why I smoked it. But it did protect a little bit. But in the meantime, I put it all back together, and I wasn't getting out the values I was expecting. So I started pulling all these parts off. I pulled off all these transistors, I pulled off all these resistors, this op amp, everything, except for this 10 megohm resistor. And whenever I'd measure the voltage on this side of that resistor, I was always getting about half of what the input voltage was. And I couldn't figure it out. It seemed to me like there was some type of resistance, like with solder flux or something at the 5 megohm region. So I cleaned this board off really well, and I did a bunch of stuff, and I fussed with this little section of the circuit for about 2 hours. And then I pulled my head out of my ass, and I remembered that the input impedance on my multimeter was 10 megohms. So the input impedance on it, as well as this 10 meg ohm impedance, made a voltage divider of a half. So I kicked myself and I put it all back together. I cut a bunch of traces, so I had to blue wire a bunch of stuff, but I got this circuit working as well. Let me see what else. I've also put in this LED to tell me when the power was actually on, the battery power for the board, because I was continually soldering and unsoldering live circuits because this runs on a battery and I don't have any LEDs to show that the power is actually applied, so I put a big bright LED on here. Live and learn. The circuit's kind of robust. I've pulled off probably 30 parts on and off while I had the power on. Okay, so let's go. I want to talk about the noise performance on the A to D. All right, so this is the voltage divider here. Here's the panel voltage here, and this is the floating ground reference right here. So these MOSFETs switch in the bottom side of a voltage divider, and this is that 10 meg ohm resistor I was talking about. This is fed into a solid key circuit, and then this goes right over to the input to the A to D. On the voltage side, I have a really good noise performance. I mean, it's just like next to nothing. It's like 6 LSB, which is great. That works out to be about a 40th of a percent, which is awesome. Now over here on the current side, what I have here is here's that sense resistor, and it goes into a positive input of an op amp. So I have a little bit of a gain right here, and this is where I switch in the gain here with these MOSFETs as well. And then I had a gain of 100 over here. I picked this really small resistance value so that when you ran a lot of current through here, the temperature change or the power dissipation was 1/10 of the maximum power dissipation. I didn't want self-heating to change the temperature coefficient or the resistance based on the temperature coefficient. So I picked a really small resistor. Well, this is kind of ridiculous. This I'll never be able to solder this part on or have it done without like real clever production. So we're going to redo this circuit right here. Also, this gain circuit here resulted in a gain of about 200, and that is way too high. Any kind of noise that's out here gets dramatically amplified over here. So I'm going to increase this value and maybe make this a bigger resistor. I don't know yet. I'm going to figure that out in the next couple of days and reduce this gain down here. So what I have going on the over here on my window, this is an output. These are the output from the A to D values. There's 6 columns, or actually there's 8 columns. This first column is the raw data coming out of the voltage ADD, and then the next column is the minimum of this column and the maximum of this column, and then this fourth column here is the maximum difference between the minimum value and the maximum value. So it works out that it's a 15-bit ADD because of the polarity, and a 20th of 1% is a count of 16 LSBs. So you can see that this thing is down. It normally runs less than 6. So our voltage values, we see almost no noise on it at all. Now in the current value, this is because there's really not a voltage amplifier stage. Now on the current side, it's a little different story. This column here is the raw A to D values. This one is the minimum A to D value it sees over this run. There's about 100 samples in this run. And then this is the maximum, and then this column here is the difference. So you can see that it's got about 10 times the noise. It's right around twice what I'd really like to have. So it's about 1/10 of a percent, which is still okay for what we're doing. The good thing is, currently, right now, I'm running at about 8 amps through the circuit. And I have both the battery charger on as well as the radio. So if I turn the radio off while I'm taking the samples, I do get a lot quieter noise floor. And it doesn't seem to matter if I'm charging or not, but I can turn that off as well. So there are some things to do, but from the first pass on the noise performance, it's actually looking pretty good. I think that this is a doable solution. And the larger I make that sense resistor, the smaller this noise will be, because that gain stage on the sense resistor amplifier is going to be a lot lower. I think that's about it for today. Really on a time crunch now. I'm going to be traveling for the next couple of days. So, and then I'm taking Thursday and Friday off. So I'll probably be back in about a week with an update. All right. This is a Solom update for February 21st, 2016. Thanks for watching.